Okay, so we've got our last lecture, potentially last lecture on spectral theory. There might be a little more applications we get involved, but we have to, after this lecture, we will take a break and start to do orthogonality and the Graham-Schmidt process. And depending on how long that takes us, we might get back into the last tidbit of spectral theory, namely creating orthonormal sets out of our eigenvectors. And when can we do such things? For now, we want to finish off what we were talking about last week. This would have been last Thursday. And let me just review my notes. It looks like we kind of just finished up with some theorems and some definitions, but we haven't quite gotten into some examples. We kind of left off, what was the... Yeah, let's sort of rehash the primary motive in question we had to sort of bring to a close this topic. So we saw that, computing eigenvectors and eigenvalues can be a little tricky. It has to be like very particular. On the midterm, you guys saw the question I posed, which actually worked out nicely. I had to cook up that question nicely enough so that when you're computing these characteristic polynomials, you can actually compute it, right? It's especially with a 3x3 matrix or higher. Well, as soon as you have a 3x3 or a 4x4, well, that means the characteristic polynomial is at least that degree, at least that dimension. So with a 3x3 matrix, we have a degree 3 characteristic polynomial. And, well, how do you solve that? How do you actually find these zeros in order to find the eigenvalues? Well, if you are very clever enough, or if you cook up the right problems, then the characteristic polynomial can kind of pop out nicely and is already nicely factored enough for you. And it's not too terrible to work with. So most people did really well on the exam with that question. The other thing we saw is, well, if I have a diagonal matrix, diagonal matrices are really nice to find the eigenvalues because the eigenvalues are simply the diagonal entries, and computing the characteristic polynomial based off of that is fairly easy. In general, though, you kind of have to imagine, we could have made the problems way harder. I don't know how far back you guys can think in terms of pre-calc, but I'm sure at some point you guys learned things like the rational root theorem or synthetic division to go along with it, right? So if I cook up a 4x4 matrix and you're in general trying to find the eigenvalues and eigenvectors by hand, well, you don't necessarily have this nice factored, let's pull up the notes. You don't necessarily have these nice factored polynomials like you get with diagonal entries. You could just get some arbitrary polynomial in general of degree 4, even degree 3 is hard. And then how would you actually guess the roots? Well, you would start guessing some of the numbers based on the leading coefficient and the constant coefficient, doing some synthetic division. So I don't know if you guys remember that from pre-calc, but that process in and of itself is very tedious and complicated, let alone having to compute the polynomial from the matrix, making sure you're doing all the arithmetic correct, then finding the roots through some sort of synthetic division or other guess and check method. And then what would you have to do? Do all the row reductions to find the eigenvectors. So in general, that process, doing it by hand, is horribly, horribly hard. Luckily, actually, you guys were very good though on the midterm. I was pretty impressed. Everyone's got the row reductions and operations down. So when it came to finding the eigenvectors as well, so the eigenvalues I cooked up in the characteristic polynomial, I cooked up on the midterm the question so that would simplify pretty easily. So the eigenvalues weren't too difficult. And then the eigenvectors, I think everyone did a really good job of row reducing correctly, or, maybe there's a small algebraic mistake, but then of course everyone realized we should get at least a one-dimensional degree of freedom, 1 degree of freedom for our eigenvectors and choosing appropriate values to make it work right. Everyone did real good on that. So let's kind of continue with this idea of diagonalization. we've realized that instead of doing this general process for eigenvectors and eigenvalues, that if we can get a matrix in a diagonal form, it would be really nice because it makes this process, it makes the process of finding the characteristic polynomial much, much easier. So let's rewrite this goal question. Was kind of where we left off, and then we kind of threw a bunch of theorems down. Is can we use the principles of row column operations to transform a given matrix and I will say as closely as we can into a triangular matrix. And actually, what we're going to see is that this triangular is going to be a diagonal matrix. It's going to turn out that we can almost always get a triangular matrix out of it, which is great. But ideally, in this process, we're going to be looking for a diagonal matrix. And what we've realized is we have to be careful that an elementary matrix times A will, in general, have different eigenvalues. So we can't just perform elementary row operations, right? Elementary row operations, remember, are the same as multiplying on the left by our elementary matrices. So any elementary row operation that we perform, we can model it as a sequence of multiplications. So I think you guys had a few homework problems on this. We did some of these kind of principal questions involving that topic on exams as well. So what we realized is that, well, instead of just multiplying on the left, our solution is conjugation. So remember, the process of conjugation is to take an invertible matrix and instead of just multiplying on the left, what we actually do is multiply both on the left and the right, with one of them being the inverse. Let me check. I forget which direction. Yeah, I think we had the inverse on the left. Doesn't matter. You can have P inverse or PAP and have the inverse here. However you want to model it, those two situations are logically equivalent. So if we sort of apply this conjugation to A, then we have A and P inverse AP will have the same eigenvalues. And we also called this similarity. So if we actually give a name, let's call it B, is this conjugated matrix, conjugated A, or A conjugated by P is what you could say. Sorry, if B is equal to that, then we say B is similar to A. And so we stated a bunch of theorems last time. Similarity is very nice. In some sense, we call these matrices similar because they are similar in all of the sort of characteristic ways in which we measure matrices. Namely, all of their eigenvalues are the same, their determinants are the same, their traces. So we introduced the trace on Thursday as well, are also going to be the same. So pay attention to the traces. We won't have much time to really explore that. Traces are important, kind of like determinants. We did a lot of time with determinants, describing how determinants are this geometric property, and in many ways, a geometric, I guess, invariant, you could call it. That the determinant of a matrix gives us this notion of a volume spanned by a given set of vectors. And it gives us this, it ties into this relationship of bases and how bases give us this scale and grid for our space. And so the determinant kind of measures the per unit scale of how we're changing a grid based off of a given linear transformation. Trace is kind of similar, but it's just not as geometric. It's more algebraic. It starts to take a look at the algebraic properties and the intrinsic algebraic structures of our matrices. And so traces give us another sort of characteristic value that we can measure off of matrices that are invariant under these conjugations, these actions of conjugating. So traces, the other thing we'll learn about traces is that the trace gives us the sum of the eigenvalues of a given matrix. So in some sense, it gives us a shortcut. If we can't compute all of the eigenvalues, the trace can at least give us, well, what is the sum of all the eigenvalues? So a priori, we can kind of take a look at two matrices and measure their traces very easily and then determine whether or not, their eigenvalues are the same or not based off of whether their traces are equivalent. If their traces are equivalent, that means, well, maybe we can do some extra work and kind of compare the eigenvalues. But if the traces are different, we know they're absolutely going to be different. So take a look at traces. You should at least know how to compute it. It is the sum of the diagonal entries. Know all those properties and principles as well. So there might be some questions like that on the final. But we want to move on and actually take advantage now of this conjugation operation. So we want to see how this is going to help us in finding eigenvectors and eigenvalues. So the example we want to start with is going to be a matrix. And now this is going to be a matrix with numbers that are fairly large. And so not only are we dealing with the problem that it is a 3x3 matrix, which means the characteristic polynomial is a degree 3 polynomial. Now the numbers aren't quite nice to work with. So instead of just straight up subtracting our lambdas from the diagonals and then computing a determinant and setting it equal to 0, that would be rather lengthy in terms of just mental computation. So we want to try to take advantage of this principle of conjugation, but we just have to be careful. We want to do it essentially kind of like our row ops, except we have to do it on both sides of the matrix. So let's kind of write that out. We want to so try row ops, multiplication on left. But also include our column ops. And that's going to be multiplication of the inverse on the right. So we can use our elementary matrices to get a sequence of matrices as long as we're performing the one operation on the left and the inverse operation on the right. That will apply this conjugation method. So I guess I don't want to write it out, but hopefully everyone can kind of check that if I take a matrix and conjugate it by P, so take A and then send it to P inverse AP, and then take that matrix and conjugate it by, say, another matrix Q, we'll get Q inverse, P inverse, A, PQ. That it's still going to be equivalent to a conjugated matrix. So we can do a sequence of conjugations and it will still overall be a conjugation. And then the other thing to note is try to get to row-esh form. But what we're not going to worry about the ones for leading entries. What are the main principles we want to take advantage of with this row operation process is getting zeros below whatever the leading entry is. It doesn't matter if there's ones on the diagonal or not. And in particular, we should probably expect there not to be all ones because what do we want? We want a diagonal matrix. Or I guess we should say we want a triangular matrix. And so even if the entries, like from our example on Friday, even if the entries aren't one, we still know that the product of the diagonals, or at least each diagonal entry, is going to give us an eigenvalue. So we should expect different eigenvalues that aren't one. So we don't necessarily want ones in there, but maybe it'll be nice enough to shrink the numbers as much as possible, right? We want to get this 33 maybe as close to 1 as we can, or try to get it as small as possible based off of some row operations from the other entries. So what do we want to do? Let's try to write this out. Unfortunately, I think this example is going to take us a little while to get through, since I do want to go through it a little carefully. So what do we want to do? We want to multiply here. Sorry, let me just write it out in terms of our row operations. First of all, we don't want to switch rows, because if we switch rows, we have to do that on the right as well, which means we would have to switch columns. You can do that if you want, but it's almost kind of like an extra step that isn't entirely necessary. Again, since we don't need absolute ones on the diagonal, let's keep the matrix as it is and only stick with row operations, primarily of type 3. So let's do -2 row 2, sorry, -3 row 2, and then add that to row 1 and replace row 1. Now, the thing is, we have to do this with our elementary matrices. So this is going to be, I'm just going to call this our E1. This will be our first step. And how do we come up with these elementary matrices? We start with the identity and perform this operation on the identity. So our identity has ones on the diagonal. And then I was taking 3 times row 2, -3, and then adding it to row 1. So it should look like that. Zeros everywhere else. So that's the elementary matrix. What would the inverse be? So these are coming up again. I think this was the point where everyone struggled a little bit. We learned them the first week and we didn't have a whole lot of time to test on them. And they kind of come up again in small doses on some of the other exams and some of the other topics. And now they're going to be much more important. So I think some people were kind of struggling going from especially defining these and then let alone finding the inverse. So you kind of have to think that I want to undo this. So namely, if I added -3 to row 2 and then just stuck a -3 in here, well, now I have to add 3. Finding the inverse of these matrices, of these elementary matrices of type 3, where we're adding a scalar multiple of one row to another row, can be a little tricky. And so I claim that it's going to be this. What's this matrix going to do? This matrix, well, aside from calling it an inverse, what's its actual operation, if we applied on the left, would be to take 3 times row 2 and add it to row 1. So this would add 3 to row 1. This one would subtract 3 to row 1. So if I did them consecutively, it would be like adding 0 to row 1. So they're going to undo each other. This is how you determine the inverses. And so now what we want to do is then compute our E1A, E1 inverse. So those are our elementary operations. And now, of course, we were interpreting this to find the inverse. If you interpret this guy as a row operation, interpret this guy as a row operation to find the inverse. However, now that we're going to be acting on the right, it will end up being a column operation. So let's see what's going to happen with this. We will have 1, -3, 0, 0, 1, 0, and 0, 0, 1. And let's write out our matrices, all these big numbers. One, 3, 0, 0, 1, 0, 0, 0, 1. So let's do this first two first. We know how this is going to act. When I multiply this row by this column, it's going to take -3 times 10 and add it to that 30. So we will have a 3 there. First row, second column, again, it's going to be -3 times 28 plus 105. So now we got a little bit of work to do. That's what? Going to be -60 and -24. So -84 plus 105. Let's do a little scratch work bubble here. What's that going to give us? 21. So we still got 21 there. We'll have, so 90, -90 and 105 will give us 15. And then we still got all the numbers in there. 28, 30, -20, -60, -62. 1, 3, 0, 0, 1, 0, 0, 0, 1. So some of these first multiplications might be a little slower because we're kind of whittling down these big numbers. Let's go ahead and keep going now. Now, acting on the right, you kind of have to think in terms of column operations. How do I get this matrix out of a column operation? It's actually 3 times column 1 plus column 2. So that's what we should expect. If I take 3 times this first column now and then add it to the second column, it's what's going to result here. Now notice that the nice thing about this, even though we're basing our operations of how to simplify this matrix based off of our typical row operations, and then even though we're doing column operations by acting on the right, those column operations aren't going to get in the way, right? Our goal was to reduce this number here. And then we'll eventually try to get rid of these numbers. But since now we're reducing this number, and now what this column operation is going to do, it's going to affect this second column, which is fine because right now our goal is simplifying this first column. So let's go ahead and multiply that out. We'll have first row times the first column is just going to give us a 3. First row times the second column, it's going to add, let's see, so 3 times 3 is 9. And then we are adding 21 to that. So that's going to give us a 30 there. So we added 3 times column 1 to that guy. And then the last column, it looks like we will have our 15. And now we'll have to go through this again. So this entry will be a 10. If we actually look at our last entry, so bottom row, first column, negative 20. We expect this middle column to be the one that's affected. So when I have middle row, middle column that we're multiplying, 10 times 3 gives us 30, plus 28 will give us 58. And then our last row, middle column, gives us negative 60 minus 60. So is that negative 120? And please, someone catch me. If I miss a minus sign on one of these, sometimes you just forget to write it when you're recopying the matrix. And then the last row shouldn't change. So if you do the multiplication, we'll see we'll get a 30 here and then a negative 62 here. So a little bit nicer. I've got a smaller leading entry there. And then now we just got to keep on chugging. So let's try to work through this quickly. Our 3, 30, 15, 10, 58, 30, minus 20, minus 120, and minus 62. Looks like we will have to use fractions. So notice at the first row, we can factor out a 3, but you got to be careful with factoring those out, because remember, even multiplying a given row by a given value is a matrix operation. So if I factored out the 3, it would be a factoring matrix on the left, but the factoring matrix on the right would undo that. And so we'd have that multiple of 3 over on the right. So be careful with those matrices of type 1 and type 2. In general, with this process, I would say stick with operations of type 3, meaning adding scalar multiples of one row to the other row. Okay, so this is where we are at. Let's do step 2. Here, let's do 2. And then what do we want to do? Let's go ahead and get rid of this negative 20. So our E2, what do we want to do? Let's go ahead and keep the first row the same. Keep the second row the same. And then let's add 2 times row 1 to row 2 to row 3 to replace row 3. So, sorry, I'm not even writing out the elementary matrix. I'm just actually doing the row operations. And this is what happens, because it's very similar to row operations, right? So what is the matrix corresponding to that? And then we'll do the row operations in multiplication. We've got our diagonal entry. We want 2 row 2 to row 3. It's going to be this guy here. Everything else zeros. And so this will be our E2. And then we want to find E2 inverse. If we added 2 to row 2, multiplied 2 row 2 to row 3, to undo that, we add negative 2 row 2 to row 3. So that we have both of those operations done in tandem. We will have 0 copies of row 2 added to row 3, and it won't do anything. And then we apply these row operations by multiplication. So we've got 1, 0, 0, 0, 1, 0, 0, 2, 1. On our matrix, so 3, 30, 15, 10, 58, 30, minus 20, minus 120, minus 62. And then we've got this multiplication on the right. So hopefully when everyone kind of saw how these multiplications are starting to work and starting to make sense of the row operations that multiplication by these elementary matrices do, and then the column operations as well. So we can go through some of these calculations a little quicker. What are we going to get? Well, we are adding 2 times row 2 to row 3. We can just simply do that row operation. We know all the other entries are going to be the same. We don't have to multiply each row. So we can be a little quicker with our calculations. I know I'll get a 0 here. We'll have 2 times row 2, so it'll give us 116, and negative 120 is going to give us negative 4. And then we will have 60 and negative 62, and negative 2 there. Let's be a little careful with this guy, since maybe we're not quite as comfortable with column operations yet. But if we would want to interpret this, now how do I get this matrix from column operations on the identity? So if we just started with the identity, I would have to take negative 2, column 3, and then add it to column 2. So that should be the operation that this guy is going to perform on this matrix. And of course, that replaces column 2. So we can go through the multiplication again. Row 1. Hopefully you can see that this 1 here in this first column, it's only going to pick out these first entries. So row 1, column 1 just gives us that 3. Row 1, column 1, give me 10 times 1, and then a 0 here. Row 2, column 2, we are going to have 30, and then negative 2 times 15 gives us a 0. All right, so we're expecting negative 2 times this column to be added to this guy. So that got rid of that guy for us, nicely enough. Now, second entry, we've got 58 minus 60, negative 2. So 58 minus 2 times 30. And then now what do we have? We will have 4 plus a 4. So again, nicely enough, these examples have been worked out so that we don't have to do too many operations to get them. And then if we check what's going on in the last row, we should see that it just picks out the last column. This last column shouldn't change. So we do 15, 30, and negative 2. So everyone see that? Let's take a look again. If I take this column and multiply it by negative 2, and then add it to this column, it'll be negative 30 plus 30 gives us a 0. Negative 60 plus 58 gives us negative 2. And then positive 4 plus negative 4 gives us that 0. Other columns, not changed. So now we're looking pretty good. This is our step 2, and it looks like we will only need one more step. So remember, the goal is only to get it to a triangular matrix. So we only have to get rid of these 3 entries. If we get zeros in these guys, we're good. We can then compute the eigenvalues off of this guy. So nicely enough, that operation took care of 2 of them for us. And so we only have to get rid of this 10. And so now with our resulting matrix, 3, 0, 15, 10 minus 2, 30, and 0, 0, minus 2, our step 3, what do we want to do? We want to do 1/3, negative 1/3, row 1, add it to row 2. I guess not 1/3, 3 1/3. What do we want? 10/3? Yeah. Negative 10/3, row 1, plus row 2. And then we are going to add that to row 2. What is our matrix? We'll call this E3. So we have our identity. We are adding negative 10/3, row 1, to row 2. Our E3 inverse would be to add positive 10/3, row 1, to row 2. And then so now we're going to compute, let's just summarize some of these. Let's call this our B2. So instead of writing everything out, let's kind of shorthand some of the work, because we're going to compute E3, B2, E3 inverse. And what is that going to be? So we can kind of just, instead of having to write out all of that, here's some maybe shortcut ways to write out your work. If we are writing out this matrix multiplication, I know these two are what we're going to do first. It's going to do our row operations. So let's go ahead and just do the row operations from this matrix. We will have 3, 0, 15. And if you want to write out the row operation again here, you can do that to keep track of your notes, keep track of your work. So that's what we're doing. So we will have, of course, a 0 here. Row 3 isn't going to change. And then we are taking negative 10/3, row 1. Sorry, let me get that on screen. Adding it to row 2. So that'll not change this entry here, the middle entry. And then negative 10/3 is going to be what? So a third is going to give us, it'll be what, 50 and 30? Negative 50? So negative 20. So a third of 15 gives us 5 times 10 is 50, along with that negative 50 plus that 30 gives us a negative 20 there. So we know we're here, but we're going to keep track of our work. We still need to multiply by the inverse of that. So sorry if that's not on screen there. So I just did the row operations. And now nicely enough, we got our diagonal matrix, or our upper triangular. We just have to remember still to do the inverse here. And if you want, you can write out the multiplication, or we can think of it now in terms of column operations. This was a matrix that we arrived at interpreting as row operations to find the inverse. If we now interpret it as column operations, how would we get this column operation from the identity? We are taking 10/3 column 2 and adding it to column 1, replacing column 1. So if we do that same operation, 10/3 column 2 plus column 1, and then replacing column 1. What does that tell us? That tells us that the second column and the third column aren't going to change. So those are easy enough to just write down. And then now we just have to perform this operation on column 1. So we take 10/3 column 2 and add it to column 1. Well, what is that going to do? Uh-oh, this looks like it's getting in the way. Because now we're going to have this -2 over here, and we definitely don't want that. Let's double check. So we should not get something that gets in the way, I don't believe, with just doing row operations. So we had 10/3 row 1, negative 10/3 row 1, add it to that, to column 2. That's giving us a negative 10/3 here. But the problem is that this column operation is now giving us something else here, and that's going to take away from our triangular matrix. Let's see if we can work this out. So we've still got this 3, 0, 15. And the problem now is we want this diagonal matrix, or at least the upper triangular matrix. But the problem now is our column operations is getting in the way of that. So sometimes we have to be clever in resolving that. So what is that going to get us? So we've got 10/3. It'll give us a negative 20/3 though, plus 0. Still gives us a negative 20/3. here. And then, of course, we'll still have a 0 here. So that is not working. So this is, in general, our procedure. And it looks like in these last steps, we're getting in the way of ourselves. And it looks like we should have done all of everything from column 2 from the get-go. The problem is any row operation that we act from row 1 to row 2 is going to be an equivalent column operation from column 2 to column 1 now. And so the other thing we want to look at is potential linear combinations of 3 and 2. That will work out. To get rid of these values. So we've got a 10 here. Yeah. All right, this one's a little tricky. Everyone see the conundrum we're in? So we wanted, for the most part, when we first start doing these column operations and row operations, we proceed as usual. We proceed as we would like to do these row operations. And then for the most part, we expect that the column operations aren't going to get in the way, namely that the column operations aren't going to undo the work we're trying to do in our typical row reductions, right? However, this is the conundrum and the problem with conjugation in general. Unfortunately, it's not as nice and not as straightforward as just straight up row reductions. So everyone's great at row reductions now. Now you got to kind of be just a little bit more clever. So this didn't work out for us, right? We wanted to end with a zeros all in these 3 entries. So this one did not work out. I'm just going to kind of put an X there. Let's keep our work, right? If you do something like this on a midterm, keep your work. Don't scratch it out just yet, because maybe it'll come in handy. But let's kind of put that to the side. Let's go back to step 3. Let's go back one step and take a look at what we had. Because we're real close, right? We've got zeros. All we got is this 110 to get rid of. And this 10 is going to be a little tricky. And what's our problem that we're running into? If I do a row operation on column 1, so like 3 times column 1 or negative 3 times column 1 plus column 2, we saw that that matrix, the inverse matrix that we have to apply on the right, well, then it applies something from column 2 into column 1 and will affect that same position column-wise. So knowing that, we've got to be clever with this position, with getting rid of this position. So our question now is try to get rid of the 10 by the same linear combination let's say the same multiple with a linear combination we should say with the negative linear combination of row 1 and column 2. This kind of just is like, this is where your cleverness comes into play. This is where you're in a linear algebra. It's an upper division math course. Hopefully a lot of the arithmetic you're solid with, and it's kind of like general, just being able to see problem solving. So for example, here I have 3 and minus 2. Now, by applying these matrices of type 3, a few things to notice. The inverse is essentially always the same as the matrix we're trying to apply, except there's a negative, right? The multiple we're multiplying by is just different by a sign. And of course, the other interpretation we've been talking about is, well, we have to interpret this now as a column operation. So we are affecting this column by a multiple that is going to be negative by this row by whatever multiple, and we need those multiples or the linear combination of those two numbers to get 10. Anyone see it? What's our multiple? What we want to do is to take 2 times row 1. Sorry. Let's write out the elementary matrix. 2 times row 1, add it to row 2. How many copies, or what's our entry in row 1 going to be? I'll have 6.
We're doing -2.
Added to that. Yeah, we want that one negative, don't we? So that guy's going to be negative. Then our inverse will be the positive. So -2 times row 1 gives us -6, and then we will have 2 times column 2, which will give us a -4. So let's go ahead and do that. We will have now our E3. And again, let's call this guy a name. Let's call this B2 since it was after step 2. So we want to compute E3, B2, E3 inverse. What is that going to do when we apply E3 to B2? It'll be -2 row 1. Row 1 plus row 2. Sorry, I'm in the wrong spot. So we'll have 3, 0, 15. And then we will have 4, 0, or sorry, -2. And then this entry here will actually be 0 as well, since we will have -15 plus 30, or -15 times 2 plus 30. Still need to do E3 inverse. And what is E3 inverse going to do? This was 2 column 2 plus column 1. So now from here, let's take 2 times column 2, add it to column 1. So we'll have a 3, that'll give us a 0 there. And then all of the other rows, all the other columns aren't going to change. And so this guy is triangular, which is great. That's what we want.
What about the 15 in row 1 when you added it?
What do you mean? For this operation here?
Yeah.
Plus row
Did
2.
I just?
Yeah, so that was back here. So our original matrix.
Oh, sorry, I missed that.
Yeah.
Yeah,
So I did -2 row 1 plus row 2. It got rid of that 30, and it got rid of, or that 10 became the 4 here. And then we did the column operations. All right, so everyone got all of the work, all of the notes down? So if you want, like if you're turning in all of your pages for the exam, like if you had this page, I did each step on a page in and of itself. I think a lot of people did this on the exam as well. Anytime you find an eigenvalue, to find the corresponding eigenvector, it seems like people used an individual page for that. It's kind of an easier way to organize your work. But we know this step didn't quite work out for us, so I'll just go ahead and put an X through it. I wouldn't want that graded. I will actually upload it to the notes for the lecture videos just so people can kind of follow along the thought process of what you might try, where you can run into hiccups, and then how do you resolve that. So a little bit of a fancy technique we had to use. And now that we are triangular, we can go ahead and find the eigenvalues. And actually, I'm just going to go ahead and write it out. So now we don't even have to, I mean, you could subtract lambda and take the determinant, but we know our lambda is going to be 3 minus 2 and 2. The characteristic polynomial is going to be the product of factors on the diagonal. So our characteristic polynomial of A, whether you want to keep it as x or non-x, you put a lambda there if you want to write it as like 3 minus lambda or 3 minus x, minus 2 minus x, and then the other factor is 2 minus x. Now, the eigenspace for each of these eigenvalues is always going to be at least 1. So we know that not only is the dimension of the eigenspace going to be 1, but because of the multiplicities of the root, that's as high as it can be. So this was something, I think most people got this question on the midterm. Whenever you have multiple eigenvalues, so if you have, if it were a 2 here instead of a -2, we would have the eigenvalue of 2 appearing twice, meaning it would have a multiplicity of 2 in the characteristic polynomial. That doesn't necessarily mean that the eigenspace is of dimension 2, so you got to be careful with that. But in this case, because all of the degrees are 1, we know that the dimension of the eigenspaces have to be at least 1, because there's going to be an eigenvector corresponding to those eigenvalues, and that's the most they can be. So we know that the dimension of each of the eigenspaces has to be 1, so there should only be a one-dimensional or 1 degree of freedom in terms of the set of vectors corresponding to each of the eigenvalues. I'll leave that to you guys. Check the eigenvectors if you want. Most people were pretty solid with that on the midterm, so I don't want to go through that again. But the eigenvalues now, much easier to determine rather than taking the determinant. And I know that example took us a while to get through, but I think, as we kind of moved along, it gets quicker, right? Doing these multiplications, especially as soon as we interpret it as row operations. We don't have to really multiply out the matrix. We can just do the row operation and then do the column operation and just keep track of everything. And we can move a little bit quicker through our calculations and simplifications. Then a little bit of a tricks in that last step. Okay, so let's kind of summarize some of these results now. Actually, maybe we do one more thing. Let's go back. This will help us lead into this next section. So we've only got, 15 minutes of class? Let's go back. Let's take a look at what we did. Since this will help kind of hit home the next point of the next theorem. So we performed a sequence of column operations. Let's go ahead and rewrite everything. So we had our A, and we had 33, 105, 105, 10, 28, 30, -20, -60, and -62. And let's see. So let's keep track. Our E1 was 1 minus 3 0, 0, 1, 0, 0, 0, 1. Our E2 was 1, 0, 0, 0, 1, 0, 0, minus 2, 0. And then our E3, the first E3 we tried was not good. The E3 we arrived at that helped us was 1, 0, 0, minus 2, 1, 0, 0, 0, 1. And then, of course, we had their inverses, E1 inverse. Same matrices, just change the sign on that one spot. All right, 1 there. And then, so how did we conjugate? We applied all of the E's on the left. So we did E1 first, then E2, then E3. And then we did E1 inverse, E2 inverse, and E3 inverse on the right. So this was our conjugation. And then what did we arrive at? Our end matrix was 3, 0, 15, 0, minus 2, 0, 0, 0, 2. Now, this is a pretty nice matrix, right? We can compute the eigenvalues. Now, I just said I'll leave it to you guys to compute the eigenvectors. And you're all pretty comfortable with doing that by our traditional methods, by subtracting 3 and then computing the determinant and coming up with your degrees of freedom. But we just did all this work to try to get the matrix in a very nice form. The other thing that we may want to ask is, well, can we determine, let's say more easily, determine the eigenvectors from this? We got ourselves a nice matrix going, easy enough to find the eigenvalues. Does the nice matrix help us find eigenvectors? Maybe not by the standard method. Standard method we could do, but in some sense, what have we done with these operations? The idea is, well, what is this information of these conjugated, these matrix conjugations, and what is the net result of these conjugations? What sort of information is encoded in these operations? And I actually claim that the eigenvectors are going to be that what's encoded. So I'm going to say the eigenvectors are encoded in the conjugation. And let's take a look. So I think this will be a good example. We can arrive at some of the big crux of these diagonalization theorems. Since I don't want to prove it, but we will see what's happening. Well, we've actually got one more step to do. This is a nice matrix. We got our eigenvalues, but it would be nicer if that 15 wasn't there, right? Then we have a diagonal matrix. So I don't think we've defined that. We've defined symmetric matrices, anti-symmetric matrices, triangular, upper triangular. So we can just sort of define a diagonal matrix is both an upper triangular and a lower triangular, i.e., we give a matrix where aij is 0 when I doesn't equal j. So on the diagonal entries, they don't all have to be the same. They can have different entries on the diagonal, but everything else is 0. So pretty much like the name sounds. It just has non-zero entries on the diagonal. And we got really close, right? Well, maybe we can just keep going. Let's do one more row operation, one more row column operation combination, and try to see if we can get rid of that 15. So in the 3-3 position, can we get rid of that? Let's go ahead and rewrite our matrix. So 3, 0, 15, 0, minus 2, 0, 0, 0, 2. And maybe we want to be careful. So first thing we might try is, well, we got to do something with row 3. So do something like 15 halves, row 3, negative, plus row 1. What would that give us? So let's call this guy our fourth step, E4, is going to be minus 15 halves, row 3 plus row 1. What would the inverse of this be? I'm afraid we might have the same thing happen that we had with our third step with E3. Well, this is going to be 1, 0, 15 halves, 0, 1, 0, 0, 0, 1. And if we were applying this as a column operation, that's going to be now 15 halves, row 1, plus, or sorry, column 1, plus column 3, and we are replacing column 3. And so what's going to be our problem? Just like in E3, like in these last steps, we seem to be getting in our own way in some sense with the row operations and column operations. You can kind of avoid that with the first steps, but as we kind of get down to these last steps, we got to be careful. Because I would add some combination of row 3 to row 1. Well, that would hit this first spot. Sorry, I guess I labeled this position wrong. It was 1, 3, right? In our 1, 3 position. So this one would have effects on that position, but then this one here would almost undo those effects as well. So we got to be careful. What we want to do is essentially the same thing we did to get rid of this 10 and see if we could get rid of this 15. So again, what are we looking for? We are going to add some multiple of column 1 to column 3. And at the same time, we are going to add a multiple of row 3 to row 1. And so those are going to be the same multiples, but negative. So we got to just be careful. Check low multiples, of course, is the good idea. If we want to get close to 15, but not equal in column operations, well, we could try 5. Of course, that would give us equal, but then I would have 5 copies of this 2 coming up. You check 4, 3, hopefully should be the one that everyone's seeing. So negative 3 times row 3 plus 15, that'll give us how many left over? It'll give us 6, and then 6 times that 2 plus that should get rid of it. Um, so it sounds like we're off by a minus sign, yeah? So that's actually not going to work. Um, so let's take a look. What are we going to have? We're going to have t times 3 plus that negative multiple times 2. And we need to get 15. So what is our multiple going to be? Sorry, what do we need to get? We need to get negative 15, I should say. So that tells us that our t is minus 15. Let's see if this will work. So that'll give us, yeah, that should work. So a little tricky here. Everyone kind of seeing what I'm doing? Let me know, should I explain it a little better? Yay, nay? Or just do it? So real quick, RE4. We know we need to get rid of this 15, so we should have some multiple of row 3 up here, right? So we know that's going to be our matrix. We're trying to find this t value, and then we know our E4 is going to be the same thing except with a minus t, E4 inverse. So this is saying take t copies of row 3 plus row 1. This is saying take minus t copies of column 1 and add it to column 3. And so what is this matrix? If I take t copies of row 3, that's going to give me t times 2. And then this copy is going to be minus t. Here, let's write as plus and negative t times column 1, which will give us 3. And then what do those have to do? They have to get the negative of this. We want it to kill that 15. So we want it to equal to minus 15. And so when you solve that out, you can solve for what your t value has to be. And so here we'll have negative t is 15. So minus t equals minus 15. And so we should get 15 and minus 15 for our multiples. So if our t, so I think we want that t to be our negative 15. So let's go ahead and write this out. We've got 3, 0, 15, 0, minus 2, 0, 0, 0, 2. And then in this column, we are going to have 1, 0. And then this column is going to do, this one we want our 15. So we'll have 15 copies of 2. That'll give us a 30. But on this side, we'll have a negative 15. So this will give us negative 15 copies of 3, which will give us a negative 45. So negative 45 and 30 gives us negative 15, and they'll negate that one. So multiplying it out, if we did the first two, we'll have 30 plus 15. And now column operations, we'll have negative 45 added to 45. And now we have a diagonal matrix. So let's rewrite out what we've got. And I guess we will have to conclude our result tomorrow. So let's go ahead and write it out. I'll get a new sheet going and we can just continue our notes for tomorrow. We have our A. And then let's go ahead and write out our matrices, our E1, 1 minus 3, 0, 0, 1, 0, 1. Our second operation, 1 here. Looks like I missed it on that other page. Our E3 was minus 2 there. And then our E4 now had a 15. And so what we showed is that A is a diagonalizable matrix. And moreover, if we take A and perform these operations, these row operations, and then, of course, we are conjugating, so we also have to correspond the column operations. And then we got this diagonal matrix. And so what we will conclude with is the fact that these matrices, in particular this guy, give the eigenvectors. And so since we already did all that work to get it into at least a triangular matrix, if there's only a couple more steps to get it diagonalized fully, maybe you want to do those steps, and then it'll be easy to just multiply those out, especially since they're elementary matrices, and then we can get the eigenvectors from that. Any questions? Okay, so that example took way longer than I wanted to, but that is how some of these examples go, especially with explaining each step, explaining my thought process of how to approach each step. I hope you guys kind of understand that and kind of can pick up on the problem-solving methods. But as we get going, as you do more examples of these, then it's just a matter of kind of plug and chug, right? As soon as we know what row operations we're doing, finding the inverse is pretty easy, determining the column operations based off of that, and then going at it to just start the simplification. The last couple steps in terms of getting a diagonal, got to be a little clever with. Hopefully everyone kind of understood how to, if you can't eyeball it, you can't kind of see, like we did with E3, we kind of just guessed it. And then if you want a little more rigorous way, if you know you got to have a multiple of one row or one column to the other, but we don't know what multiple that needs to be in order to get this conjugation to cancel out one of the entries, you can always just do a little bit more rigorous problem solving methods to find what that value needs to be. And we wanted to keep track of that specific matrix now, because now when we multiply these matrices together, or at least when we multiply their inverses together, it's going to give us the eigenvalues. So we'll draw our conclusion with that tomorrow. And then also tomorrow, hopefully we will start in with the Gram-Schmidt process. So that Gram-Schmidt, not too bad. Usually pretty easy to do, but we'll have to remind ourselves about orthogonality and linearly independence and bases and all these types of things. All right. I'll see you guys tomorrow.